I will probably spend about an hour going through slides, and then we can turn this into a discussion after that. And as indicated, if you guys could use the microphones for questions, that'd be great. So I'm going to tell you what this talk's really about on the next slide now. So let me tell you a little bit about myself, a little bit more detail. I work in the office of the CTO at Network Appliance, and my role is twofold. One is tracking technologies, much broader than just storage, if you don't know NetApp or a storage company. But I track technologies much broader than that. So I look at server virtualization, I look at network advances, I look at high-performance networking, et cetera. Bring that with a customer flavor back into Network Appliance, and then also am sort of a voice out to our customers and the press and analyst community about what we're doing, what we're thinking, architecture, direction, vision, things like that. So that's sort of my role. As indicated, I got a lot of background in sort of big data, big compute problems. Initially high-performance computing problems, scientific high-performance computing. Then really moved into sort of large data warehouse, data mining applications on big shared nothing architectures. And then about the last 10 years, a bunch of consulting in scale-out Linux systems, Beowulf-type clusters for bioinformatics. And then the last 5 years really been concentrating on storage, because I think that's really the hot area right now. We've sort of gone through, and I'll talk about this sort of the last third of the talk, but we've gone through a a high-performance computing revolution, moving from mainframes to SMPs to scale-out, 1U, 2U boxes or blade systems. And I think we're right on the brink, actually, of seeing a similar transition in storage that I think is really exciting. And so I'll touch on some of those things. I'll touch on some of the challenges from an operational perspective over the next hour. And hopefully you'll find this of interest, and I'll leave plenty of time so that if I don't hit your hot buttons or your areas of interest, we can talk about it at the end. So that's the plan. See if we can get this going now. That's the outline. So I'm going to talk a little bit about, so first off, a lot of people have definitions for grid computing. I'm going to give you 3 in a minute, but I'm going to focus on what I'll call enterprise grid computing. This is sort of the utility computing model, agile IT infrastructures, things like that. Not necessarily high-performance computing, but I will tie some discussions to that. Talk specifically about what's going on in server and storage virtualization, and then really talk about how you put those together to really develop what I'll call virtual application environments, so end-to-end virtualization, right? And then we'll wrap up with some thoughts on future of storage, which really is all about scaling out storage architectures, what that brings to you, and then moving to a much more distributed storage architecture with distributed services. So that's the agenda. Don't like it, you can get up and, no. That's what we're going to do. So in the enterprise, and some of the slides up front I'm just going to hit real quickly. The slides I will make available to you guys. But the key issues when I talk with customers across the board, and again, I'll focus right now on enterprise customers largely. Huge data growth, right? 50, 80, 100% a year is not uncommon. Increased globalization through mergers and acquisitions, or sort of spreading the organization out to new areas, especially in the Far East, China, places like that. So globalization is rampant. Everybody's out to reduce capital expenditures, operational expenditures. This is sort of the do more with less concept, and it's really key, especially when you're increasing the amount of data and the complexity of the operations that you're doing with the data, and I'll talk about this in a minute. But we're in a world now where the pressures on data management are growing incredibly fast, and IT budgets are flat, right? So you got to be able to figure out how to manage that beast. Disaster recovery, business continuance. I'll talk about this when we get into virtualization, but virtualization, whether you're talking about virtual servers or storage consolidation, means you've got many applications hosted on one physical piece of hardware, one physical storage device, one physical server. And it means if you have an outage, even if it's to do an OS upgrade, you're taking out a dozen apps, right, or 16 apps, and you can't do this anymore. So you'll hear everybody talk about non-disruptive upgrade, non-disruptive operations for servers, storage devices. We'll talk about that both in the virtual server environment and the storage world. I won't touch much on security, but intellectual property compliance litigation is a concern for a lot of enterprise companies. And then one of my favorite ones is how you improve business agility, right? So how you turn around applications much more rapidly, and I'll talk a bit about that. On the right-hand side, sort of a lot of technologies that are kind of hot. One of my favorite ones here, and we'll talk about this at the end, is the notion of DAS bricks as storage, right? And if anybody has looked at things like the Google FS architecture or other architectures like that, pretty interesting model, which is a massively parallel storage system built on literally commodity server/storage components. Pretty potentially game-changing. I'll talk a little bit about that at the end. So I said I'd define grids. There are technical computing grids, or what you call high-performance computing grids. There are actually data grids. In fact, this is really the origin, the Ian Foster origin of the term grid was really about how you distribute data and computational resources and other resources, instrumentation, for example, if you're looking in a high-energy physics environment, across a large geographical area and also multiple ownerships, right? That's sort of the data grid model. And then I'm going to talk mostly about optimization grids, which really are about utility computing, on-demand computing, better resource utilization, consolidation, moving towards distributed service-oriented architectures, or what in general I would call a more nimble IT infrastructure. And I'll define that in a second. The only thing I want to make one point here, which is I think an enterprise grid, it isn't something you go buy. It's a set of technologies and how you use them, and it may be different for different institutions, okay? Its goals are well aligned with sort of the bullets on that first slide that I had. So I want to just take a couple of slides and give you what I think of as the sort of key tenet of enterprise grid computing and utility computing. I think this is maybe not today, but certainly in recent past, the model, certainly in large enterprises for deploying applications, was you identify a business problem, find a set of applications that you buy, build, or integrate. You size your servers and storage in anticipation of peak demand. You go provision them, or procure them, provision them. When you're in dev mode early on, your utilization is very low. When you're in maintenance mode for your applications, towards the end of the life of applications, your utilization is very low. If you guessed right, your utilization is good in the middle. If you guessed wrong, you either paid for hardware you're not using, or what's usually more painful is you're outgrowing the devices that you procured and need to figure out a way to get to a bigger platform. Very painful in the storage end because it usually means data migration and service outages. And you do that again and again, right? That's sort of the old model. And what enterprise grid computing is really all about is taking that back end, replacing it, in essence going to a utility-oriented model, right? Where you've got a bunch of much smaller commodity-oriented components, servers, networking, and storage, that really is the foundation over which applications are provisioned, re-provisioned, migrated for service level adherence and those sorts of things. And that's really the vision, at a 50,000-foot level. So I'm going to go through this front stuff pretty quick, and we'll get into a little more meat in a minute. This is sort of a picture I use that's sort of my sort of big picture of what I think what's involved in enterprise grid computing. On the left, you've got server virtualization strategies. That might be things like VMware, where you're going to have multiple applications hosted on a physical server, one physical server. Might be things like Oracle, RAC, 10G, 11G, whatever you want to name it, where you now have applications that can spread across servers, right? A database server that can spread across physical servers to improve performance as application requirements grow. And you might, and then looking forward, this is really where service-oriented architectures are going, right? So this is literally distributed applications, portions of which get instantiated dynamically, mapped to hosts or portions of hosts, and basically a find and bind model from the client perspective, whether it's through WSDL or more of a client-server model, where the applications go find the instances of the services. You can instantiate new services if you need more performance, if you need more capabilities, and it's a much more dynamic application development model. And that's really where we're going. We're sort of, I think, certainly in the infancy of some of that, at least in terms of a lot of the customers that I talk to. But that's the vision of being able to leverage that server farm, that commodity-based server farm. On the right-hand side, you'll hear a lot of people in the storage world talking about tiering, right? And that usually means making a decision about high performance or low performance disk and trading off the performance for cost, right? Is the usual thing that people talk about. But there are a bunch of other subtleties there as well that are really more service level oriented or service level requirement oriented. So how you're going to back up and recover that data, what your RPO and RTO are, what levels of compliance you're going to apply to that data, retention periods, and ensuring that it's not touched, it's not modified. There's sort of a whole suite of characteristics, if you will, of data. And as we go forward, that suite of characteristics is actually growing. This is a little bit what I talk about in terms of the complexity of managing data these days. It's not just sort of online, offline, right, online and archive. There's a whole range of tiers of storage these days that have performance characteristics, different security characteristics, et cetera. And so we'll talk a little bit about this in the next few minutes as well. There's a virtualization pain similarly over storage, because what people want to do, and a lot of people call this a global namespace in the NAS world, but what people in essence want to do is separate the logical path to the data from the physical location, right? So that you're free to move data around on the back end non-disruptively with respect to the application, right? And this is really the part of the panacea of getting to a grid architecture like this, where you can actually change the service level characteristics of data over its life cycle, right? And you'll see on the next slide that's a little bit the mantra of information lifecycle management. But that's really the key, I think, from a storage perspective. People talk about file and block virtualization. If you're interested in the details of that, I'd be happy to share that with you. But this is things like Acopia, Neopath, which was bought by Cisco. They do sort of an in-band file virtualization scheme. There are block virtualization devices as well that basically allow you to migrate blocks from one tier of storage to another non-disruptively and transparently to the application. That's what virtualization is. Caching is an interesting layer here, and it's really hot in a few areas right now. In the internet services or Web 2.0 space, caching is huge right now. I've got a bunch of customers, very, very well-known household names, Yahoos and Facebooks and all of those guys who are making extensive use of distributed memory caching architectures, things like Memcached in particular. And so you're seeing this whole layer right now of caching architectures, and with the upcoming flash revolution, flash SSD revolution, I think you're going to see this area explode. It's also interesting, we tend to think of it at NetApp as really almost an approach to reverse HSM, right? So if anybody's tried to implement an HSM solution, hierarchical storage management, those systems have tended to work in environments where you have a very high ratio of data to metadata. In other words, where you have relatively few very large files, satellite images, maybe medical imagery, things like that. They don't work very well or at all, and they don't scale if you're in environments with lots of small files. So if you're in like a home directory environment and you want to do file level virtualization and migration, in other words, you want to migrate individual files that haven't been touched in a while, or migrate MP3s, whatever policy-based migration you want to do, but you want to do it on a file-by-file basis, and you want to leave the namespace exactly the way it is. There are techniques for doing that called stubbing, where you basically intercept the opens or the creates, and either pull a file back from a tertiary storage device and then serve it to the user, is typically the way it's done, transparently to the user. So the user thinks he's opening a file. What he's actually doing is causing a data transfer to happen from historically a tape system into the file system, where he can then read it locally. It stays around for a while, and then it gets aged out, right? So interestingly, caching does very much that thing, but it's sort of in a reverse fashion. So rather than pushing data down to a lower tier of storage explicitly based on its age, et cetera, I have customers who are looking, and these are big customers. So for example, Yahoo Mail, We've got about 40, I don't know, last count, 40 plus petabytes of storage there for mail archival, for mail history, or anybody has Yahoo Mail accounts. They keep your mail forever, right? Well, most of that stuff after 10 or 20 days is never touched, right? So historically, what they've done is sort of push data down from a primary tier after some period of time into a secondary tier, into what I'd call a cheap and deep tier of storage. But there's a lot of interest with them and others in this concept of putting data initially down on the cheapest tier. Now I'm talking about spinning disk now, so I'm talking about large SATA systems that are really cheap and deep. And if you look at disk drive prices these days, you can get a terabyte for, I don't know, 300 bucks or something like that, terabyte drive. So you're down into 30 cents a gigabyte arena if you look at just raw disk costs. Now, by the time you put it into a system, add resiliency and things like that, it's not in that arena. But a lot of customers that I have who are looking at very, very large stores are expecting to be able to deploy at somewhere around the $1 per gigabyte or $1,000 per terabyte arena, or a little bit more for large-scale storage systems. And so their thoughts are, just write the data there to begin with and cache it forward. So as a user accesses it, cache it and maybe do some intelligent prefetch based on the application. Cache it either into faster disk or potentially into flash or even memory, depending on what your application requirements are. Let it be accessed there, age out, get basically ejected from the cache, and it's sitting on your cheapest tier of storage. And that's actually something that we're looking at a lot right now. It's a pretty interesting model, especially with flash coming, starting to come into play. You're also in a grid environment. I think you typically today see it sort of in a data center context. But over time, I think you'll start to see this in what I'd call a cloud, right? So it's geographically distributed. And if you look again at things like Google's doing with Google FS, and some other companies are doing with very, very large data stores that need to be accessed from multiple POPs. They're looking at building these clouds with replicated data across physical sites in the cloud for a combination of resiliency and improved data access performance. So I think you're starting to see some pretty interesting things in that space over the next few years as well. I said I'd go through this fast, and I haven't yet, but we'll get there. ILM, sort of the old word, but it's basically the concept is is really managing that back-end storage tier and doing it through automation and policies rather than having storage admins explicitly move data, right? And doing that completely transparently to the application, right? You don't want applications to go offline simply because the data moved. You don't want applications to lose track of where the data is because you want to move it down tier. It's to do this automatically. People in the database world want to do this as well. They want to do either partition level or row level archiving. You'll hear people in the database world talking about this. Very common theme right now in terms of moving to very cheap bulk storage for data that you have to keep around but that you're not using. And basically this is about how you get the right data, the right service level at the right time for the right price. And it changes over time, right? Applications have a profile where data has very high value initially and falls off over time. I'm not going to go into, I'm going to skip through the next 5 slides really quickly. One of my colleagues is giving a talk tomorrow at 11 on policy-driven management of data sets, which really goes into this in a lot more detail. Fundamentally, the issue is right now we're in a model where storage managers are the bottleneck, right? If I got in an enterprise environment, if I got to deploy a new application, you got to make requests to the storage management guys. They got to provision it for you. They'll get back to you with it. There are, in a lot of organizations, that's a fairly challenging process. It can be a time-consuming process. It really slows down the application development cycle, or what I talked about earlier, called agility. Because, frankly, there just aren't all that many storage admins. Everybody's trying to do more terabytes per storage admin, right? The storage admins are supposed to be doing more stuff because they actually have to now worry about different service levels of the data and what tier of storage they're going to put it on and how they're going to back it up, and they got different tools for doing that. So the goal really is to simplify that whole process and to really delegate a bunch of the storage management capabilities under watch of policy. And so it's really this notion of application admins or application development managers being able to set the properties on data, right, in terms of how important it is, how frequently it needs to be backed up, what its RPO and RTO are, for example, whether it needs to be encrypted or not, at what level, at rest or on the net, et cetera. And then the storage admins are really responsible for creating processes around policies that are predefined, that can get assigned to those, what we'll call data sets. And if you listen to my colleague tomorrow, you'll hear a lot more about that. This is just a simple example, probably a trivial example for most of you, but you think about data set, it's got some recovery time objective, it needs to be secured in some fashion. In this case, it's got a low RTO or zero RTO, which basically means you need to do synchronous mirroring. So that would be an attribute of that data set. It would automatically set up a synchronous mirroring relationship to a target that was on an appropriate system to do that. It would create, in NetApp parlance, what's called snap lock, which is in essence a worm-oriented volume. It's got a retention period, so you can't go delete it or modify it. And in this case, you'd be enabling encryption on it, right? So this would set up, when the application developer sort of creates this notion of a data set, it actually gets mapped to physical entities or storage pools that are out there that have the appropriate service level characteristics. And that's all done by policy. But the application admin can actually do this under policy. They've got some, in essence, they've got delegated authority to basically go create storage according to a set of predefined policies and you know, clearly with predefined capacities and things like that. So that's really the vision of where we're going. Again, I'll direct you to that talk tomorrow. And I mentioned most of these items in here, but we basically do policy implementation and enforcement just above the storage, and you do delegation from the application managers, from the storage manager to the application managers so that they can actually do this. And you don't have that bottleneck in the storage admin pool, but rather you've got application admins who are doing this themselves. So, and there's been work in this in the past. This isn't, this sort of isn't de novo work, but it's something that's really important to us. And again, I'd encourage you to, if you're interested in that, to go see Costados' talk tomorrow. So I'll switch gears now. This is sort of 3/3. That's the opening third. Talk a little bit about server and storage virtualization now, and then we'll talk about some of the trends that I see in the scale-out storage arena. So let me define first storage virtualization, because virtualization is one of the most overused terms I've ever heard in the computer industry right now. Our founder actually defines it kind of well. He says virtualization is about making something you have look like something else, right? And at a 50,000-foot level. In the storage stack, there's a bunch of places where I think you can apply that term, right? So disks are typically rolled up into RAID groups, which are rolled up into volume groups or LUNs, so that you don't have to worry about individual disks. You now worry about LUNs, which is sort of a pseudo disk, right? It's a big fat disk. It's got data protection associated with it because it's got RAID 5 or RAID 6 or RAID DP in our case or whatever. At the volume and LUN level, you have this notion of thin provisioning people talk about, which is, somebody needs a terabyte of storage, you grant them, quote, a terabyte of storage, but it's thin provisioned, right? So it's, sort of the way banks work, right? They don't, if they've, well, basically it's the ability to give out more storage than you physically have, knowing that people underutilize and grow over time, and you'll provision just in time, right? So that's what thin provisioning is about. So it gives somebody the view that they've got a terabyte LUN, even though the physical storage that's backing it is likely very much smaller than that. Dynamic and expansion and contraction LUNs. Snapshots and clones I throw into this arena as well. A snapshot is a point-in-time read-only copy of a file system or LUN. I'll talk about this in more details. A clone is actually a writable copy. I throw them here because they can be virtual. In other words, they don't have to be fully instantiated copies to still be a point-in-time copy. I'll talk about that in a minute. I think this is really important. There's virtualization at the controller level. You can now take LUNs and stripe those, or you can take multiple LUNs to create striped volumes across them. They may live across controllers. Some people call these meta LUNs, call them striped volumes. There's virtualization at the protocol level if you're going to use gateways. So you have block devices on the back end, but they've got NAS gateways in front, so you're doing sort of protocol translation. It's actually SAN storage, but it's serving out NAS protocols, right? And then I'll talk a little bit about virtual storage servers in a minute, which is the analog of sort of virtual servers in the compute world, the VMware sort of model. There's fabric-oriented virtualization these days. People are doing replication and migration either in the fabric or in appliances in front of the controllers. There's aggregation and namespace stuff that's done there, again, like Acopia, Neopath, Rainfinity, Attune, if you're familiar with those. Caching and WAFs is some stuff that's done in there as well, again, which I would roughly throw into the virtualization arena in terms of delivering you data that looks like it's close, but it's really far away, right? And doing it with low latencies because it's caching or it's doing some smart protocol acceleration. And then at the host level, you've got some aspect of that as well, where you want to do, certainly in an ESX environment, you've got at the host level, you've got virtualization going on in terms of multiple images and multiple applications. So I want to dive into a couple of these in a little more detail. I want to talk, so this is a NetApp specific slide, but the concept in general is being used more and more widely in the industry these days. So if you think of, and the way that NetApp does it has historically been pretty unique, and it's kind of clever, so I'll go into this in a little detail. But it has to do with the way our underlying storage subsystems are written, called waffle, and the way we use NVRAM, non-volatile RAM, and the way we do RAID. So let me describe it just real quickly. If you think of a file system now, this active file system in the middle, and it could either be a block device or it could be a file system, a NAS file system, NFS or CIFS. You basically have, at one level, the inodes or the block maps, right? The indirect blocks and things like that. And then at some point down on disk, you actually have the physical disk blocks where the data lies, right? And that's the ABC down there, which is supposed to look like 4 blocks on disk. So I got an active file system alone. It's got 4 blocks on disk. And at a point in time, I can take what's called a snapshot, and I can take a clone. And a snapshot is a point-in-time read-only copy of the file system in NetApp technology that's actually done almost instantaneously with no physical copying of the data blocks. We basically copy the root inode, and that's it. And now you have a snapshot. Clones are the same way. They're writable, though, which is kind of cool. So we'll take an example here. Let's say this is a database. The active file system is a database. We took a read-only copy and a writable copy. Again, no data copy when I take those. Very, very quick, almost instantaneously, no data copy. Now my database, which is in the active file system, is going to do an update, right? So what are we going to do? We're going to replace a block on disk. We're basically going to update a row, which is sitting in a block, and that block needs to be replaced on disk. Well, in the way the NetApp system works, we actually don't do a read, modify, write, or what's called a copy on write out to a separate location. Because of the way Waffle and NVRAM work, we just write a new block, and then we go change the block maps or the inode pointers, basically, or the indirect blocks in the inodes. So we write one block to disk. It's this new block X. It's sort of owned by the active file system, but neither the snapshot nor the flex clone see it, right? Because it's not in their block maps. Their block maps didn't get updated. Okay, do the same thing with a clone. So the clone's a copy of the database. He's now going to do an update to a different block, or actually to the same block on disk. Maybe the same row, maybe a different row. He writes one block to disk, okay? We now have 3 entirely distinct, from a logical perspective, file systems or LUNs, in this case databases, and all we've done is accumulate 2 blocks on disk, okay? And when I first talk to people about this, we go through three stages, right? Typically they don't believe it, that it's true. They then think about, if this is really true, this sort of changes the way I do a lot of stuff. We'll talk about this in a minute, database dev test in particular. And then when they see it, the change is pretty phenomenal. Now we aren't the only company that are doing what I would call virtual snapshots and clones. I think we're the first in both of those, but we're not the only company anymore. But the way we do it, I think, still is pretty distinct. So so it's a really important concept, especially as we start to talk about rapid deployment of applications. So I wanted that as a foundation because I'm going to be talking about snapshots and clones in particular in a couple of scenarios going forward. The scenarios I've listed here are things that I typically hear about companies who are deploying, again, these sort of enterprise grid environments, agile computing, nimble IT infrastructures that they talk about. They want to do very rapid, efficient application provisioning, right? Often with centralized image management, right, where you got the OS and drivers and app stack in a centralized image, and historically you'll do a push out to the boxes that you want to provision or update, and the reason you do a push is it's really costly to keep n copies of an image on shared storage. I'll talk about that in a minute. More and more people are looking at going to network boot environments, right, where they can actually go to centralized storage environments, and I'll talk about why clones actually makes this cost effective, okay, the clones that I'm talking about. We'll talk about application cloning for dev, test, QA and how that changes, just really completely changes the dev, test, QA cycle. It can also be used for data warehouse, ETL stuff out of band of the production databases. I'll talk about that in a minute. Business continuity and disaster recovery. So how you do backup and recovery, replication services, failing over to your DR service are traditionally services that people want in this environment as well. And then what I'll call virtual application environments. And this really is leveraging the promise of the VM world by augmenting it with, so if anybody knows the VMware product or capability called vMotion, which is the ability to migrate a running process from one physical server to another. I'm going to talk about dmotion, which is the same thing on the back end. It's how do you move your data from one storage system to another non-disruptively, because more often than not, it's actually the back end that is that gets bottlenecked, not necessarily for example, the ESX server. So we'll talk about that. First thing, and again, some NetApp specific slides, but this stuff is going on elsewhere. So again, some key concepts, even if the slides say NetApp. This is something we've got in RTP in North Carolina. It's a system we call the KillaClient. It started with 1,000 nodes. I kind of joke it really should be called KillaFiler. And if you know NetApp, you know that our storage devices historically have been called filers. This is a facility we use basically to beat the living tar out of filers all day long, all year long, right? It's our test facility. And we got about a 2,000 node cluster now. We've actually gone with IBM Blade server approach. So we put, basically, in essence, have sort of a best practice or operational guideline, which allows us to build this system up in sort of sets of pods or sort of building blocks that we can sort of scale out. And a pod is 16, 14 node Blade servers, a 3050C, which is one of our storage systems in a failover configuration, some networking, appropriate amount of networking. And we started actually doing this initially about 3 or 4 years ago with Fiber Channel HBAs, diskless boot. We moved to iSCSI HBAs for diskless boot. We're now, the last round of nodes that went out with standard NICs and are doing iSCSI boot. I think we're actually using the iBoot stuff from IBM, but there's other technologies out there that use sort of the PXE DHCP model of sending the information, the IQN basically out to the device when it boots, so that it can bootstrap itself by mounting the iSCSI device or attaching to the iSCSI device and directly booting from that. We create what we call golden images, and a golden image simply is an OS, a version of an OS, a set of drivers, a set of applications, right? It's your application environment. We put those into a LUN, call it a golden LUN, and then when we want to go diskless boot a machine, what we do is we actually create a clone of that golden LUN. So as I mentioned before, the clone is instantaneous and basically just changes some block map pointers, no data on disk. It doesn't do a full copy of the image, right, on shared storage. When that image gets personalized, which is scripted to push the IQN in it based on it hitting the DHCP server with its MAC address, that additional information is now new data on disk, right? So basically you can create literally hundreds of copies of that image. Each one is unique, and each one can be independently booted from, but all you've accumulated on disk are the aspects of that image that are distinct from the clone, right? So you can do this very efficiently. It's actually, I think, one of the reasons why shared storage booting has not taken off is because without a mechanism like this, it's not cost effective, right? Shared storage for n copies of an image is just too expensive, right? So people have these push models where you take your image and you push it out to multiple hosts and then do a, if it's a Linux, you'll do the boot configuration, right? This allows you to do it in shared storage. It provides some neat benefits. We've used it extensively We also can take those cloned images and store them off into a repository to bring them back later, so we can sort of preempt testing and bring it back, or we can go do some testing later. We're evolving some scripts around that. We've been working pretty closely with a company called QLusters that has that's built around the open source project, openqrm.org. It's a company that came out of what's called the Distributed Resource Management, or DRM community, which historically has been job schedulers for high-performance computing environments. Those companies now are broadening into the enterprise and managing resources other than compute cycles, right? So they're managing, in particular, images and storage and things like that. So we're working pretty closely with those guys to try and productize this into a sort of centralized image management, diskless boot product, right? So working on that stuff. And I won't go into any details on this. This is sort of my view of the world on iSCSI, and I'm sure I'll get, a bunch of different opinions on this. But my take on the way iSCSI has gone, is going, is the first wave was really about opportunistic cost reduction for existing DAS servers. So you got a bunch of SQL servers and file servers, Microsoft file servers sitting out in the net. They're all at 3% CPU utilization, and they're on old hardware. And what you want to do is somehow consolidate that, right? So you bring each of those images, in essence, comes in as a LUN on a shared storage system. iSCSI out the front is fine performance-wise, easy to deploy, and you go to town with that. And now you're basically in a consolidated storage environment. We've seen a lot of that sort of the first couple of years. That was sort of this big ramp up of iSCSI. Sort of flattened out a little bit, I think. Certainly people continue to deploy now in this sort of middle bubble, what I call business essential applications, not mission critical, but applications that, if they're down for 30 minutes or so, it's not so critical, and they may not have the ultimate in terms of transactional throughput requirements, right? So you see people putting reference databases, reporting, data warehousing, some mail messaging and collaboration products, et cetera, on iSCSI. We have a lot of customers who put, in fact, very large Exchange installations on iSCSI, and you're starting to see this more and more. Things like the Linux iSCSI software initiator being distributed as part of the kernel instead of an add-on or a download from SourceForge. Some stuff Microsoft's done around multi-connection sessions, which allow you to get improved performance using multiple GigEs, enhanced error recovery. Vendors putting iSCSI on board, software boot. That's sort of starting to snowball. I think the thing that really accelerates this is when we get to more pervasive 10 GigE, and some of the numbers coming out of iSCSI on 10 GigE are just flat phenomenal. There's a paper that was done probably a year and a half ago by a company called Naturian, who makes a 10 GigE card accelerator with a TOE accelerator, and a company called StringBean, which was later purchased by Microsoft. It's a StringBean Win target. It's an iSCSI target. It is now part of Microsoft's WUDS server, which is their next generation Windows storage server, as their iSCSI target. And about a year and a half ago, they published results demonstrating 3 clients, and I don't remember exactly the hardware, but they were multi-processor Intel boxes, hitting one iSCSI target device, which happened to be an Itanium. And the clients were getting somewhere around 350 megabytes per second apiece to the iSCSI target, which was doling out, actually it's a little higher than that, because the iSCSI target was doling out 1.3 gigabytes per second over a 10 GigE iSCSI interface. Okay, this I think really changes the game. It leapfrogs what's going on in the fiber channel arena in terms of the 2, 4, 8. We're at 4 gigabytes right now for host connect. And I think the one area sort of that still has to mature is an area that Fiber Channel has done pretty well in, which is around the management of that storage infrastructure, specifically around QoS and SLA adherence and what they call traffic shaping. But I think we're going to see that over time. I think you're going to see more and more 10 GigE deployed. There's also an effort within SNIA called FCOE, Fiber Channel over Ethernet, which if that accelerates as well, then we'll be in a scenario where we can run basically both Fiber Channel protocol and iSCSI protocol over literally the same wire, or certainly same fabric, and that's a pretty interesting development. So these are my rough timelines as when I think some of this stuff's going to mature. I'm sure everyone's got their own opinions on that. And again, that was really just, I wanted to bring that up since we talked about iSCSI and diskless boot. So let me talk a little bit about agility and database cloning and how virtual clones or flex clones in our product parlance really change the world of how you do database development, database application development. Almost everybody does database copies for dev, test, QA, training, whatever, right? And the model that you typically have to do that is you either make a full or partial database copy for your various organizations, and in a lot of cases, you do this from tape, right? You do this from the backup. So if I go to the next slide, you do either an offline copy of the database or you do an online, which potentially can affect your production system performance. It might be using snapshots and log-based consistent recovery. It might use actual database mechanisms, the database vendor mechanisms, or you'll do what's called a redirected restore, right? Which is everybody backs up their databases historically to tape. A lot of people are starting to do it to disk. And so you create actually a clone for dev or test by doing a redirected restore. You do a restore into a new instance, right? And now that's your dev test environment. Well, guess what? If you got a 200 gig database and that's coming from tape, that's a good 6-hour process, right? Which means people usually schedule it the week, in advance of the weekend, do the restore from tape over the weekend. Some poor slob who's pulling that off of tape gets to work with the DBA to set it up so that the developers have it on Monday morning. And God forbid the first thing they do is drop table, oh crap, I need a new copy, right? So lots of pain points and challenges in creating multiple copies of databases. 100% storage overhead if you're, per copy in general. The time. If you don't need a full copy of the database, then you've got the responsibility of going and writing some extract scripts which only pull the relevant pieces of the database out for your testing, and that takes time to develop itself because you got to get that right, and that's typically iterative. So a lot of challenges, right? A lot of time put in, a lot of resources put in for that. So the question around clones is, what if your DBAs and app developers could basically create and recreate consistent copies of a database app almost instantaneously with negligible storage, additional storage, at least on create. I'll talk about that in a minute. No or little support of a storage admin. That's really the model of where we want to go with what we think of as application integrated facilities or services around some of these storage capabilities, like cloning and snapshots. And so the typical model that we have customers deploying is they'll take their production database. They won't actually create the clones there because you don't want a bunch of dev test, jockeys firing up databases and doing big ad hoc queries against a copy of the data that happens to sit on the same production storage that you're running production apps. So what you typically will do is what we call snap mirror, but in essence it's a mirror, an async mirror that's done periodically to your secondary storage, to another storage device, which could actually be sitting on iSCSI and SATA drives instead of high-priced fiber channel and high-end controllers and fiber channel host infrastructure. And off of that second copy is where you create the clones, right? So the mirror that's sort of continually accumulating basically gets frozen, cloned, and then you continue the mirroring, and now you have a clone over there, which is a logical copy of the database. It happens to use the same blocks that well, I'll call it the DR copy, the secondary copy uses. And as that DR copy, that mirror continues to propagate, right, its blocks go down to disk, but the clone never sees them because it was a point-in-time writable copy, just kind of as I talked about in that earlier slide. And so you can do this again and again and again now, right? I can do this with, again, nearly instantaneously with no additional data footprint beyond whatever the developers are going to change. You can do this for a wide variety of purposes. You can do it for, again, you can do patch testing, right? You got Oracle patch testing and you need to verify your application, or you need to make schema changes and validate your application, or you got a new application against the same data. Whatever, ETL, if you're doing data warehouse types of operations and you want to do extract, transform, and load out of a copy of the production database in this case, but without impacting your production operations at end of month or what have you. You want to do end of month reporting, you can do that out of band of the production system. A lot of uses for this. We've got a lot of customers starting to deploy this. Very interesting in terms of what it can do for your development environment. Just real quick, we integrate this into what I'll call an application management tool. application integrated management tool. We call it Snap Manager for Oracle. It's integrated with RMAN. It basically is, it's not quite one button, but it's basically a, gives you the cockpit for doing this stuff, right? So cloning, make a copy of this database on that server over there and name it, name the instance foobar, right? We can actually do this in heterogeneous environments. So the last picture I showed you uses something we call Snap Mirror, which is a NetApp to NetApp async or sync replication engine. About a year ago, we purchased a company called Topio that is, in essence, a heterogeneous block replication engine. So we can actually do this from non-NetApp primary to NetApp secondary and then leverage our clones off the back end. So we can take this off of your favorite vendor's storage where you're running your production databases. We can, in essence, tap that data onto a NetApp as a secondary and then use our cloning capability to rapidly create new copies of databases, again, very space efficiently. And that can actually be done either with a host shim, which is very lightweight, very low memory footprint, very low CPU footprint, but some people don't want to put a shim on their host. Or it can be done in switch, right? So there's Cisco has an architecture they call the SAN tap, which is basically a way for you to plug in components into literally into the MDS switch to take a tap off the, well, I'll call it the block stream, and make a copy out to, in this case, to what we would call a Replicator X server. So you can actually tap it in the switch. We're doing some work with Brocade as well, but the Cisco stuff's pretty far along. This is actually just a picture of the original Topio GUI, and the 2 points I want to make here. So this is what we're actually doing here is replicating LUNs from this host on the left. These are LUNs that have actually been mounted as drives on devices on Windows, and we are replicating those to a NetApp device here, which is why you see the little NetApp logo. The binding here is what we call consistency group, right? So the Topio technology in particular can take a consistent point-in-time copy of multiple LUNs, even across multiple hosts. So if you have distributed applications or you've got database and file system-based applications that need to be kept in, where those data entities need to be kept in sync, you can actually do that consistently within that framework. The snowflake here is the result of what they call a freeze. So we basically freeze the replication session. Now that doesn't actually stop the replication. What happens, the way the Topio stuff works, is the replication ends up on the server. It sort of gets squirreled away. I won't call it scratch space, but it gets squirreled away into a holding location, and then it gets applied into the target image, or target LUN in this case, right? And so all freeze does is stop that apply operation. You're still doing the replication across the network to that target device, and then when you thaw it, basically it's got now more blocks that need to be applied all at once into that back end. It's got a global time clock algorithm, guarantees consistency across, again, multiple LUNs and hosts down to the sub-second level. So you can actually do sub-second RPOs with this. It's asynchronous, but you can do sub-second RPO with it. Pretty neat stuff. And again, useful in a heterogeneous environment. And again, this is what NetApp's doing. There are other people in the industry who are doing similar things. I would absolutely encourage you, if you're looking at stuff like this, things like this can change the way you do app development. So I'll talk a little bit about server virtualization, where that's going. This is probably an eye chart, certainly from the back. I don't know that you'll see this, but nominally, server virtualization to date has been used in dev test, server consolidation for things like DNS servers and LDAP and Active Directory and all that sort of stuff, right? Sort of infrastructure servers where you're going to have replicates of them anyway. Much less so for traditional production computing. And if you look at sort of how virtualization is evolving, server virtualization, the initial drivers were around environmentals, right? Which is, I got a bunch of boxes, burning up heat. They're underutilized, and I'm running out of space in my data center, right? So this isn't so much I got to reduce my bill by 20% a month. These are the people who are really driven by this are the ones who said, you know what? If I add another 50 or 100 servers, like my apps guys want me to do, I got to go build a new data center, right? It's a step function, right? So that's been a big driver. Consolidation for infrequently used or low performance apps, as I mentioned, often on old hardware. Often applications that are relatively old, they can't take advantage of multiprocessor or multi-threaded or multi-core environments, but that's what you buy these days because that's the most efficient use of your dollar. So virtualization in particular allows you to now throw multiple of those apps, which otherwise are sitting there using 3% of a modern day server, and use up the CPU, right? So they're utilization oriented. Or they're for platform refreshes, right? I got an application on hardware that's 3 years old, and my 4th year maintenance just went through the roof. And I got to get it off there. So you can now move those on to new boxes under new maintenance contracts that are on your standard 3-year warranty, for example. I can support my legacy apps, and I don't have to worry about it, right? As we go forward, I think what you're going to start to see is this notion of a dynamic application service infrastructure, which is really the application of this infrastructure more pervasively into the production-oriented side of the house. I think you're starting to see that, but I think it's still somewhat limited. A lot of challenges when you go into a virtual server environment. You now are replicating images in shared storage. So your OS images, if I got an ESX server and I'm running 32 OSs in there, right? I now got 32 OS images out there, right? I've got nominally, and I'll talk about some things we do there that reduce that footprint, similar to the way we do flex clones. But nominally, you got n copies of that image. I now have n times the backup traffic, because now I got to back up n images off that ESX server, and I may have a bottleneck either in the network or on the tape device on the far end, right? And you get this proliferation of VMs, right? The fact that you can create VMs or the fact that you can create snapshots and flex clones really easily, really quickly, means that organizations tend to do lots more of them. So you actually have lots more of application instances out there than you used to have, and that further stresses typically backup infrastructure. You need resilient storage-based DR. So doing it off a host, doing backups off a host is not a scalable model. I mentioned earlier this notion of vMotion, which is the ability to migrate applications from one ESX server to another, typically for load balancing, but it might also be for disaster recovery. Shared storage facilitates that. I'll talk about it in a second. Application cloning we talked about. Let's see. This is my slow slide. There we go. So in terms of DR, this is a picture where we're trying to show a bunch of VM images in the middle that would be sitting on an ESX server, hitting, in our case, a NetApp storage device running either Fiber Channel iSCSI blocks or NAS or CIFS. We support all of those. I mentioned earlier this notion of flex cloning images. It's a model that I call, a lot of people hear about dedupe in the world, right? So this dedupe is basically, if you got a bunch of data out on disk, go find all the parts that are exactly the same and reduce those down to one copy, right? And there are a bunch of different algorithms for how you do that, whether it's block-based or dynamic algorithm, whether it's after the fact or in band. There's lots of different approaches. One of the things NetApp's been doing, I mentioned earlier, this notion of flex clone, right? This ability to create a bunch of images and only have the deltas on disk. I call that no dupe. We sort of never dupe it, so we don't have to dedupe it, right? Snapshots are the same thing for us. We, for many years, have done disk-to-disk backup by taking snapshots, which are this point-in-time virtual read-only copy of the data, and propagating those to a target device. We call it Snap Vault. But all you propagate are the incremental blocks that changed, right? And what you end up on the target looks like forever fulls, but it basically has the footprint of forever incrementals. If you want details on it, I'd be happy to give it to you. But that's another no-dupe model, right? We don't ever dupe that, right? Because we take care of that on the front end by not duping stuff because of the way we do snapshots and Snap Vault propagation. We can also do dedupe on the back end. So you could take your NOS images, mirror them to the back end, and then run dedupe on them on our target, and it'll basically take out all the common blocks, which, for images would be a significant reduction. It's probably in excess of 20 to 1. If you hear about dedupe ratios of 18 to 20 to 1, most of the people who are quoting those are quoting them on backup operations where you'll do like daily incrementals, weekly fulls, and you'll do that for 18 weeks, right, or something like that. That's sort of your cycle, right? And then you roll off your fulls every 18. You have a moving window of 18 weeks of fulls and incrementals. Well, you get an 18 to 1 reduction when you do that because you have 18 fulls, and in general they don't change very much, right? There are other areas that dedupe doesn't work as well for, and it's not all that well publicized. But there are other areas that are kind of innovative where they work, like things like images on ESX servers, where they drastically reduce the amount of space that you need to store n images that are run by an ESX server. And we can, basically use DR to ESX server failover to the copy, right? So the snap mirror is sort of this repetitive operation that you run periodically every minute or so. And then your failover scenario in that case would be failover to the target, and you may actually do some log mirroring as well if you're in the database world to ensure that you can recover to more granular RPOs. Just real quick, so I will go over about 10 minutes on the material, and then we'll hit questions. But just real quick, one of the things that's really important in a consolidated virtual environment is the ability to model and ensure service levels, especially if you're going to go into production. This is actually one of the reasons I think why virtual server environments largely dev test to date, because we don't have the monitoring tools and the automated migration tools to be able to react quickly enough to oversubscription of resources in particular, right? So you need to have models of what your application service level requirements are, which are at an application level, but probably permeate the stack down, certainly down to storage. You need to know what your latencies or ops throughputs are to serve an app. You need those metrics quantified. You need acceptable ranges so you can sort of do almost a statistical process control model, right? Find out when they go out of band, alert, and then you need to be able to figure out what to do with it. And typically that means you need to migrate an application off of one physical device to another. And you may need to migrate the data as well. One of the things that we deployed a while back is, it's not a QoS, but it's what we call a control service. If you guys are Unix guys, you know the Unix nice command for processes. This is Unix nice for volumes, right? Allows us to set a priority on a volume. We'll take a disproportionate amount of the system resources, the NVRAM, the CPU, and the number of I/O transactions we'll allow in flight for that volume. And we apportion those out to ensure that we keep the higher priority volumes getting more of those resources than the lower ones, so that we can keep their response time low at the expense of less important ones. This is a property you can set dynamically, you can script it, you can calendar it, and it's kind of a nice way around at least the temporary oh crap, I've oversubscribed my storage, right? At least you have the ability to figure out who's going to get whacked by that, right? It's great in a dev test environment. Production environment, it's still maybe even a little scary, but we have that facility. I mentioned earlier vMotion, right? This is in VMware. It's the ability to take running applications and migrate them from one ESX server to another without application outage, right? Well, you got to kind of plumb it so it hooks up to the data on the back end, and more importantly, I would say more often than not, the bottleneck isn't necessarily the cycles on an ESX server because you've added too many Oracle database instances, let's say. It's probably more likely the storage on the back end, because when you bought your storage device, you didn't anticipate you were going to beat the crap out of it with a whole bunch of instances and some test instances that you've now, in our case, flex cloned or whatever you're doing. And so you actually need the analog of vMotion, which I'll call dMotion. You need the ability to non-disruptively migrate data across physical storage devices to do load balancing, right? You need to do it non-disruptively. Well, NetApp's had a product for a while. It's called Multi-Store, nicknamed sort of vFiler, because that's in essence what we do, is just like VM images, we create virtual filers or virtual storage systems within one physical filer or storage system. They've got independent management domains. They can be on independent IP subnets or IP addresses. So they really do look like a separately managed storage device. The beauty of those is we can actually do something we call vFiler migrate, which is literally taking a virtual filer, it looks like a storage subsystem, and migrating it from one physical filer to another. We can do it non-disruptively for NFS and iSCSI. Can't do it for CIFS, because CIFS is session stateful, and we're working on that. We haven't quite figured out how to do that yet. And at least right now, we can't do that for fiber channel blocks. We can do it for iSCSI blocks, and we can do it for NAS. So pretty neat. So you can do this to actually reduce the load on your source storage system, offload it, rebalance your load to now exploit this target. We can also use that as a sort of continual DR scenario. So rather than doing explicit migration, we do disaster recovery that way. We basically, again, repetitively mirror the data from one vFiler to another on another physical filer. And if we have a failure, we basically fail over the clients to that target, within timeout bounds, and we can do that non-disruptively for iSCSI and NAS again, or for NFS. So there's a bunch of stuff that I think certainly we have as a company. Some others have it. I don't think others have as full a suite that I think really help in terms of rolling out virtualization infrastructures. And again, end-to-end application virtualization. So being able to address not only the ESX servers full, but also I better get a bigger box on the back end, right, my storage device. So I'm going to spend the next 5 minutes, 6 minutes talking a little bit about future storage. And my first slide is about compute servers. And the reason is, if you look at about this is probably early 90s, 92 was the sort of inception of this concept called Beowulf, which is basically building a supercomputer using standard components, right? Standard CPUs, standard OSs, standard interconnects, mostly standard interconnects, largely Ethernet. Guys do MirrorNet and InfiniBand and stuff like that, but it's non-proprietary interconnects, okay? As opposed to something like an IBM SP2, which had a IBM proprietary interconnect in it, right? So this was sort of a new way of doing high-performance computing using scale-out server architectures, right? For apps like this. And what's really interesting, there's a site called top500.org, which sort of tracks this for the last, goes before 98. I forget how far back it goes. But if you go back to 98, so I actually took this data and extracted it and started charting by what they call system type, right? So there's SMPs. These were like the large E10Ks. Actually, HP Superdome is probably more of a constellation. Constellations are sort of these clusters of SMPs. MPPs like IBM SP2s and things like that. And then clusters, which really are Beowulf, right? So they're standard, Intel AMD architecture boxes in 1U, 2U form factors, some bladed, but basically 1U, 2U form factors, commodity components, standard network interfaces, and they are now 75% of all of the top 500, the most powerful computing systems in the world, right? 75% of them are actually on this architecture now, right? And it's continuing upward, right? You can see SMPs have basically completely gone from the top 500. They were huge for a while, right? People like Sequent and those, well, I guess those were NUMAs. Some of the NUMA architectures early on. I think SGI Altix is actually classified. I don't know if it's classified as a constellation or MPP. I have those details. If any of you are interested, you can certainly contact me. I'd be happy to share this with you. But the big point is we've seen this, there's this huge move over the last 10 years to commodity scale-out servers and figuring out how to use them to solve the world's biggest problems. And if you look at, there's a guy named Clayton Christensen who wrote a book called The Innovator's Dilemma. It talks about the fact that disruptive technologies come along every once in a while. Beowulf is a disruptive technology, right? I believe we're sort of right at the brink of seeing a little bit of this in storage. And if you look at what Google's actually put together, that 4 or 5 years ago, everybody I knew thought they were going to fall flat on their face building their own file system with many hundreds of thousands of nodes, is the estimates that I hear. Basically, a node is a motherboard with a carrier and about six cheap disks on it, 6 SATA disks on it. And you got many tens of thousands of them, if not hundreds of thousands of them. And you basically build distributed file systems on them, right? People thought, oh, it can't work. Now, admittedly, what they do with them is somewhat specialized, and they build applications that leverage the underlying Google FS architecture, and it doesn't have the full semantics of a standard NFS or CIFS file system. But for a lot of applications, it does some pretty neat stuff. Almost everybody in the Web 2.0 space that I talk to, and there are a lot of people, are looking at building their own or figuring out if there's a technology out there that does something close. There's a SNIA initiative called XAM, Extensible Access Method. It actually derives from some of the original EMC Centera work, collaboration with IBM, Sun, NetApp, a bunch of other people are in this as well, to actually define really what I think of as sort of an object store, object cloud model, right? So how do I got bits, I want to put them into the object cloud, get an OID back. When I give you the OID back, I want my bits back, right? How do you do that? And how do you do that by utilizing cheap, in essence, server storage, or I'll call them DAS bricks, right? But you can go online and you can find, if you look at Sun X4500s, you can get, I guess they're now on terabyte drives, you can get 4U, 48 drive, So 48 terabytes, and I can get it for about 60 or 65K. $65,000, right? Do the same thing with, HP's got boxes like this, right? So DL385s, you can put either, small form factor SAS drives in it, or you can put SATA drives in it. You can basically build out building blocks, which are server and DAS storage at, 10 terabytes a chunk, and you can do it for less than 15K. And guess what? It comes with 3 years maintenance, because it's a server. Basically, it's a server model of storage. And if you can build software over the top that either does file systems or what I'll call an object store system, if you're interested in, cheap and deep for mail or photos or video, YouTube videos or whatever else, you can leverage those. You can leverage the commodity pricing in the server world for storage devices. It gets to be really interesting. And granted that this is not today for everybody, but the guys who are thinking in very large scales, where what I used to say, scale matters, right? When you save a buck a gigabyte and you're deploying hundreds of petabytes, it's pretty much real money at that point. So these guys are looking at this stuff. I think you're going to see this continue to mature in some areas, probably not all. I don't think you'll see it for some time in the enterprise data center, but you'll certainly see it in what I call cheap and deep. So archival, nearline, media nearline, medical imaging applications, things where you got buku data, lots of data, and it's growing extensively, and you have sort of this object model semantics of get put, right? Amazon S3, if any of you have looked at that stuff, is a very similar model. I got some slides here I'm going to skip. I'll tell you what it is, and the deck's here, but it basically is looking at taking the digital effects business, the guys who make movies, right, either special effects or full feature animated films, Disney, DreamWorks, Pixar, all those guys. And it really looks at the trend over the last 5 or 6 years of what's happened in their shop. And I'll cut to the chase, but there's information in here about sort of how they work and what their workflow is and sort of how they've scaled. But their scale is very consistent with sort of the scaling you see on the top 500. So this is a chart from top500.org, which shows the performance of the top 500 systems over the years. And it's got 3 lines. It's got the number 1 system, so the most powerful system in the world, which is in the middle there. It's got the number 500, which is the bottom one. And then it's got the sum, right? And this is in a semi-log scale. So obviously the number 1 system sort of goes more chunky. The other 2 are pretty flat, but the slopes are pretty uniform across those. And if you actually do a rise to run, you'll find out it's about a 10-fold increase in CPU performance every 3 to 3.5 years, right? And guess what those CPUs are used for? A lot of cases it's for generating data or for analyzing data coming from more and more capable sensing modalities, satellite imagery, MRIs, whatever. Year after year, all of those devices get much more sensitive. Seismic processing, amazing some of the stuff they're doing now. They're doing 8 and 10-fold the amounts of data that they were doing a couple years ago, and it continues to increase because you can now have higher fidelity sensors and more of them in parallel, right? So the computing is basically keeping pace with the data flow, and then it's also generating boatloads more data. So it may not be a 10-to-1 increase in data, but it's probably pretty close. And so, we're seeing tremendous increase in the amount of data. We're seeing, in many cases, and this is in NetApp environments, in NFS environments, in shared SAN environments, you're seeing situations where you fire up huge Linux clusters from a compute perspective and beat the living tar out of some concentrated data sets, and literally, have one device on fire and the others are sitting there snoring. So that's really the reason to move from sort of these traditional storage architectures into scale-out storage architecture. So you'll hear a lot about this. We're doing stuff, some technology we acquired from Spinnaker Networks a few years ago. You'll hear it in a bunch of other companies, right? Isilon, Ibrix. There's piles of companies out there right now doing scale-out storage devices. Panasys, where I was for a while. And the promise of scale-out is really, going back to that picture on a couple of pages ago, is to actually spread your data out now over multiple controllers so you don't have a hotspot anywhere, and so you're leveraging all of the controllers all of the time. And there are a variety of ways to do that. But fundamentally, you're doing the same thing in the storage side that was done in the servers, right? As you're scaling out your apps, you're distributing your apps across multiple boxes to get higher aggregate performance. And I won't go into the details. There's about 3 or 4 slides in here that describe the original Spinnaker architecture that NetApp acquired and how that's rolling into a system we call ONTAP GX, which is a scalable, basically, right now it's a scalable NAS platform. It will be ultimately our scale-out platform for what we call unified storage, which is all protocols, blocks, iSCSI, Fiber Channel, NFS, and CIFS on one scale-out platform. The notion of being able to dynamically migrate volumes or LUNs across that back end non-disruptively to the client. The ability to, in a couple slides, I'll show that at least. So here's the non-disruptive motion. But we can do that now. We can non-disruptively migrate volumes which show up in the namespace across the back end, and the application never knows it. We can do that for file systems right now. We're going to be able to do that for LUNs. We can create what are called stripe volumes, which are big volumes that go across many controllers to, again, get the aggregate performance. So you get very high performance for some volumes. I think over time, what we envision happening, there are actually two parts of that architecture, and we actually see them going into more of a disaggregated model. Again, if you want to talk more detail, I'd be happy to with you. The end game there is, I think eventually we're in a much more distributed storage architecture with different services, if you will, distributed across those components, right? So we talked a little bit about SLA-based provisioning. So that would be, which storage pool you go on, which might be associated with one or more sets of controllers based on your performance requirements. The ability in the net to index, categorize, and search. Monitoring SLA adherence in there. The ability to replicate and clone, again, across controllers. The ability to migrate data, this file and block virtualization non-disruptively. But in a much more distributed, sort of service-oriented architecture. And that, you ask me time frame, it's off a ways, but that's where I see things going. If you look at the industry and what's been happening in the storage industry is a lot of in-the-net devices, right? Whether they're caching, protocol optimization, block migration, file system or block migration, stuff going into the switch. There's a lot of stuff right now going on in the network in a much more distributed architecture and a more scalable architecture, right? Where those devices can also be built into scale-out configurations, large scale-out in-memory caches, for example. You'll see this with Flash as well. So that's what I had for you. That's a little bit of where, what we're doing now, which I think is on the leading edge of some of this stuff, and then where I think eventually this is going with scale-out storage architectures, and it's I think a pretty exciting time. I used to work in high-performance computing, and if you'd have told me I was going to go work in storage, I'd have told you were nuts because it was the dullest stuff in the world. And now I think it's both where a lot of the pressure is to really be able to grow applications, but it's also where I think there's a lot of innovation going on that's pretty exciting. So. That's what I had for you. Thank you. I apologize for running a little bit over, but we got about 15 minutes for questions, and I am happy to stay around for a little bit afterwards and chat with you individually if you'd like. I don't know if my contact information is in the packet, but if you want to get a hold of me, drop me a card, and if you have a specific question or want me to get a hold of you, let me know. I apologize, I don't have my cards. They're all in Reno right now because I came from Supercomputing 07 yesterday and I'm going back tonight. But it's Moxon, M-O-X-O-N, at netapp.com. And feel free to give me an email. Thank you, and I'll take questions. So don't be shy. We have the mics on?
Well, thanks for giving us that great overview, Bruce. I think it was really helpful to understand the breadth and the depth of what's going on in this space. My question is about, for your specific products and technologies, where do you think the bottlenecks and scalability limitations will be? You talked a little bit about, say, GFS and those kind of systems potentially scaling to hundreds of thousands of nodes, and that you had roughly a couple thousand running at your business right now.
Client nodes, not storage nodes, okay. But I will address that. Okay. So good question. So when I talk about Google, those are really that's what I would call a massively parallel storage array in some ways, right? It's a lot of little storage nodes that are all independent, part of what I would call a shared nothing architecture. And in other words, each of the individual nodes is connected into the network, has local CPU, memory, and disk, but can't directly address anybody else's disk, right? You have to go through the net to do that. And so that's a massively parallel storage array in some sense. What I was talking about, the 1,000 nodes that NetApp's running, we run our server farm at those levels of scale. Our scalable storage system actually uses significantly bigger building blocks. So when you talk about parallelism and building parallel systems, one of the keys is granularity, which is sort of how big a building block do you have and how many of them you have, right? The Google is sort of to one extreme, which is lots and lots of little blocks. We have many fewer big blocks, and just for reference, our ONTAP GX system, which again is a parallel NAS system, goes up to 24 of our standard filers or standard storage controllers. In other words, the same boxes that we ship into enterprise environments, we can also ship in a ONTAP GX configuration, a scale-out storage configuration. Each one of those can do probably 600 megabytes a second. So on aggregate, you're somewhere in the 12 gigabytes per second, right? If you took the aggregate throughput of a Google file system, assuming adequate network in it, it would be far greater than that. And some of the high-performance computing systems, which are optimized towards performance and not necessarily resiliency or data protection or other things, you'll see web publications that are in the 10 to 100 gigabytes per second for things like GPFS, and I don't think Panasys is up that high, but Lustre certainly is published in that arena as well. We're probably in the 1 to 10 gigabytes a second arena now, and again, our sweet spot really sort of evolves from where we've historically come, which is from sort of technical computing, NFS servers, so people who do chip design and simulations and fluid dynamics and things like that. And it's more focused, I would say, in areas like production-oriented technical computing. So guys who use these tools on a Fluent and stuff like that on a day-to-day basis to get products out the door. Bioinformatics companies or rendering houses that basically are doing, in essence, production-oriented computing is probably where we're a little bit more focused. And there's sort of ends of the extreme. If you look at, Google's sort of probably you sort of look at a dimension along those lines, and if you go one way, you're in very, very high aggregate performance storage, and if you go another way, you're in very, very cheap and deep performance, right, which is low dollars per gigabyte, huge capacity sort of stuff. And we have a range in there. We're sort of in the middle. We're looking at how we expand that, but we're sort of in a sweet spot that I'd say is more enterprise, mainstream technical computing oriented, not some of our guys inside call it the lunatic fringe. I don't think it's so lunatic because I came from there. But I don't know if that answers your question. Okay. Yeah. Yeah, so I think if you really want, so if you wanted to build a Google FS clone for some of the things they do really well, and one of the things they do really well, right, so they do, they index the web all the time, right? So they basically have this huge, massive array of bots that are going and collecting website stuff, pumping it into this massively parallel storage system, and then indexing the hell out of it, right? And they use highly distributed computing techniques like Hadoop and MapReduce, if you want to look those up. But they're operations that are meant for that sort of computing environment where each of the individual pieces is probably going to be linearly scanned, okay? And then you're performing some sort of aggregation and transformation operation in the net, for example, to aggregate up the indexes, and then writing back out to also a parallel storage system. It's a different type of operation than traditional file systems and certainly block devices for things like databases. If you look at NetApp storage systems today that are based on ONTAP and Waffle and things like that, we are probably a better architecture for the stuff we do, for the enterprise stuff. It's not clear that we would be optimized for the type of workload that Google does at that scale. Now, that having been said, there are applications like data warehousing that sort of look kind of halfway in between. They sort of need the resiliency and data protection characteristics that has been one of our strong suits and things like cloning, but they do need high performance sequential I/O. We're looking at that. We're trying to figure out, we have some internal R&D projects to look at Waffle, which is our underlying storage layout system, to make some optimizations of that for some of these other workloads, right? So if I characterize Waffle right now, it's a really innovative architecture for optimizing, in particular, writes without a major penalty to reads, but it is definitely not a read, what I would call a read-optimized file system. And if you look at some of the stuff out here that's trying to be massively parallel, these guys are in what I'll call the fixed content space, right? Which is, you write an object into the cloud, you don't ever change it, right? You don't ever do an update to it, right? I don't do an open append at the end, right? If I want to modify it, basically I blow that one away and create a new one, right? In fact, that's the XAMPP semantics specifically. Every time you modify an object, by definition, it gets a new GUID, right? So we're looking at some things that are more optimal for those models, right? Which have different access semantics, right? The fixed content stuff in particular is usually one writer, okay? Probably no concurrent readers, right? It's an atomic operation. You either write the object or you don't. Once the object's written, people can read it, but nobody's going to ever write it again. So you don't have this single writer, multiple reader concurrency issue of locking and things like that. It's a much simplified transactional model of how you actually put data into a storage system. Waffle's not optimized for that. We are looking at how you make those changes. That's one of the key areas that I think we have to look at if we're really going to go to that level of scaling. Because as you indicate, there's a lot of stuff in there to deal with, multiple concurrent accesses into single files, semantics for appends with multiple writers, all that sort of stuff that you don't need and you want to get out of the way, right? So we're looking at stuff like that. We're also looking at, stuff that's being done externally as well. So, and I probably can't go into a ton more detail, but if you want to chat offline, we can do that under NDA. I can talk to you about some of the projects we're doing. But we are doing some projects along those lines. Yep. Fundamentally, to answer your question, if we took an ONTAP GX system and built 1,000 nodes, we'd have some scalability limitations. So, today, not the goal. Other questions? Given my lengthy answer, I think we probably only got one or two more anyway. So.
Hi. I was wondering if you could comment on the perspective more from sysadmins and customers in terms of data center virtualization and data center management, particularly on service-oriented.
Specifically what?
Specifically service-oriented.
Service-oriented? You mean in SOAs, like web services architectures? Or?
No, from sysadmin perspective.
Like I was talking about, okay.
Yes,
yeah.
In terms of what's the pain point of sysadmins.
So let me hit that on a couple of fronts. And again, I'd suggest if you're interested in this in more detail, 11 o'clock tomorrow in Reunion AB, it's policy-driven management of data sets by Kostas Roussos, who's my colleague. He'll go into more details in some of the concepts that I talked about up front with reducing the bottleneck to storage administrators and doing sort of self-service storage and things like that. I can tell you today it's really early, okay? We have grand visions, we've got some stuff in place, but it's still pretty early in terms of actual deployments. And in fact, just to be really honest, something like FlexClone, which I talked about for database dev test QA, I sit down and have a discussion with app developers and DBAs in large financial institutions. We have about a 10-minute discussion, and it's like, light bulbs are on, okay, let's go, how do we do this? And then we spend about 6 or 9 months actually working through them with the operations guys to figure out what stuff we need around the edges that they need to deploy so that they can actually delegate the authority to roll this stuff out, monitor it, and ensure that they don't have sort of runaway rogue users. So to directly address your question, that is an area we're hotly engaged in right now. I don't think we have all the answers, but again, I think Kostas will be able to tell you sort of where we're going direction-wise. And I think that's probably pretty typical in the industry. I think it's certainly with features like this, I think that's pretty typical in the industry. Features like FlexClones, features like what I talked about earlier as vFiler Migrate, which I basically put in the same camp. Great technology, great sort of raw technology. We think it's potentially a huge marriage to VM environments, but how you integrate that into a ESX management console or vice versa, how we integrate with an ESX management console on the storage side. That's stuff we're working on right now. It's not sitting in product. It's not, we don't roll that out with FUBAR 1.0. Right now we do a fair amount of work with engineering and professional services, and what we're trying to do is take those experiences and roll those forward into product. That's very similar to what we've done with the Killa client in particular, where we've taken the work that we've done with QLusters, and we're in the process now of building a 1.0 product for image management and provisioning. That will be basically single instance provisioning, raw hardware provisioning initially. Over the next 6 to 9 months, that will then roll into also doing VM provisioning. So it's early, we're starting. But that's the vision we've got. I think we're in, there's some other companies out there that do some cool stuff in this space, historically, especially in the provisioning arena, but with more of the push model. And there are companies who do some very cool stuff, companies like Anaro, if you're familiar with them, and some of the other ones. But the industry's maturing. It's not going as fast as everybody like. One of the things that still continues to be a challenge is storage management per se, despite initiatives like SMIS and Asperi, which is a Eclipse-based storage management project. The vendors have a lot of vested interest in their own management tools for their own storage, right? For a couple of reasons. One is those tools can expose and facilitate access to their value-add features. But the other one is definitely a little bit of a selfish nature of ensuring the propagation of their species, if you will. And so I think you've seen, if you've looked at the storage management arena over the last 5 or 6 years, what you've seen is a few companies pop up and get to a point where they're basically acquired by an HP or an EMC, or I actually don't know that we've actually acquired one, but you've seen that happen over the last few years. And then those tools end up they'll still do some heterogeneous management, but it's optimized for their platform. And so in particular, a tool, even a third-party tool, a CC store or something like that, is not going to be snapshot and FlexClone savvy on a NetApp to actually be able to integrate that into your operations very well, whereas tools we develop will. And so there is a little bit right now of sort of a compartmentalization of functions by whoever owns the management tool, which is whoever owns the storage that they're selling with it. We'll see how SMIS is going on a little slower than people had hoped, and there at least are provisions there for both the standard set of services and also vendor extensions. Asperi, I'm a little less familiar with these days. Custatus might be, if you're interested and you get to chat with him tomorrow, he may be able to fill you a little bit more in what's going on in a cross-vendor sort of direction with things like Asperi. Hope that answered your question. Okay. One more?
My question is about storage tiering.
Yes.
At the moment, if you build different storage tiers with NetApp, then if you have a changing customer environment and changing needs, then it's usually costs some downtime actually to migrate certain usage of a tier to a different tier.
It may.
It may, but if you use Fibre Channel LUNs, for instance, then it can be fairly difficult.
It can what?
It can be fairly difficult. So you really have to sometimes really throw the stuff down, at least for a couple of seconds, to quickly do things. So you get close.
Right.
Even it will always be disruptive. So
yeah. So even if you're going to put one of these in-band boxes in, and Rainfinity's one, right? So they do blocks, they do a lot of EMC stuff, as well as I think they do NAS as well. But basically, that box when it goes in, you have a short disruption, and then now you're set up to do either migration or in-band. Although most people don't actually continue to use that in-band; they use it sort of for a one-time migration. Yeah. But you do. You take a hiccup, right?
No, but I'm more curious about the view of NetApp about what your approach is regarding ONTAP, because I think with ONTAP you can be very close to the effort, and I don't want to buy additional hardware sitting in between as an extra line.
So that's you just hit right on one of the, and I'm sorry if I didn't make this clearer, but that's one of the main reasons that we bought Spinnaker Networks, is they have what I call a switched storage architecture. I'm sorry I didn't go through that slide, but basically there are two components to that. There were two pictures, something we called an N blade and a D blade. Those sort of sit in a single controller. They're separate functions. They're really modules. The end blade terminates the access protocol. Right now it's NFS and CIFS, but it'll be iSCSI and Fiber Channel down the road. In the file system world, there's something that we call a VLDB, a volume location database. You can think of this as a volume router, okay? Very much like a network router, right? Which takes path or FSID and turns it into a target, what we call D-blade. So the D-blade's actually the guy who talks to the disk and talks waffle and serves up the data. The end blade talks to the D-blade via a lightweight RPC protocol called SpinNP, right? Which is protocol agnostic, right? So the end blade terminates the protocol, does a SpinNP, gets the data, returns it back. Again, very lightweight, very quick switching, very much like a router. That core technology is fundamental to where we're going for exactly the sorts of things that you discussed, for the ability to non-disruptively migrate volumes or LUNs across back-end controllers,
or CIFS,
or stripe
whatever.
them, right? So, or convert them from non-striped to striped if you need aggregate performance of multiple controllers. That's exactly why we bought that company.
Okay.
And
Thanks.
you know, it's hard. So people ask us, why is it taking so long? Well, it's hard, and I think we're going to be in a spot when we get there. We're going to be in a spot that I think is unique in the industry. We'll own it in the controller, you know, on the controller side. You know, jury's still out. Cisco is certainly trying to own all that stuff, right? The switch vendors are trying to own a lot of that stuff, and in essence commoditize back-end storage, right? There's a lot of discussions going on that. Oracle's trying to commoditize back-end storage. The new 11G DNFS, direct NFS, you know, allows them to have a high-performance NFS client dialed in, can take advantage of multiple links, and as long as you talk v3, and I don't know if they support v4 yet, NFS v4, you know, they don't really care what it is, right? So their game is to sort of push their functionality down the stack with replication and everything else. VMware, same game, right? They're trying to push down the stack, right? They're trying to take ownership for more of the storage functions, whether it's replication for DR or what have you. So you know, it's not a done deal anywhere. There are a lot of people playing for that, for what I'll call that virtualization piece that's sort of somewhere between the controller and the network, and that's why my slide specifically had the bracket that said it's blurring, right? Because there's a lot of players going after pieces of that with different approaches. Appliance, in the switch, SAN tap type stuff, at the controller architecture.
Yeah, we'll see where it's coming at.
So
in a
yeah.
couple of years. Okay, thanks.
Yep. If you got a crystal ball, I'd love to see it. All right.